Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, WA campus. These lectures have been edited from the two sources given here. The topics that would be discussed in this lecture are string manipulation instructions, and in particular instructions compare string, scan string, load string in store string, string instructions. String manipulation instructions are instructions of the microprocessor or instructions in the instruction set of microprocessor that are responsible to manipulate string data. String is basically a sequence of bytes or words that are stored in the memory. And in 8086 and above microprocessor, their instruction set includes different instructions for a string movement to move strings from one place in the memory to the other, and also to compare string data, to search or scan string data, to load accumulator from the memory, and to store accumulator into the memory. There is a repeat prefix instruction for the instruction that is used as a prefix of string instructions, and this repeat prefix causes string manipulation instructions to be repeated a number of times depending on the value in the counter. Let me highlight them. Okay, so then there are some letters used with string instructions. These letters are S, S, B, S, W, and in later microprocessor there are letter S, D, and S, Q. So basically the letter S means that the instruction is a string instruction. So for example, simple data transfer instruction is MOV, that means to move data. And if there is a S, then that become a string manipulation instruction. For example, move S is a string manipulation instruction. Move and move S are quite different from each other in the sense that just move instruction cannot transfer or move data within the memory from one memory location to the other, but move S string manipulation instruction can move data within the memory. SB means that the instruction is a string manipulation instruction, and B stands for byte. So the byte instruction is operating on byte of data, string data. And W means word, and if there is a D, then that would mean double word, and if there is a Q, then that would mean quad word, which is 8-byte data. Similarly, just like other microprocessor instructions, effective address or the offset needs to be used to calculate physical address. So in these instructions, normally the effective addresses or the offset addresses of the source operand and destination operand are stored in the source index register and in destination index register. So string instructions normally either have two operands. One is the source and the other is destination, and in that case SI register would provide the offset address for the source operand, and DI would provide the offset address for the destination operand. And if there is only source, then SI would be used. If there is only DI destination, then DI would be used in the segment, or for SI, when SI is used, normally the source of the data is the data segment, while destination of the data is normally extra segment. Similarly, as repeat prefix is normally used, that causes the instruction to be executed multiple times, and in that case the offset address needs to be updated to point to the next higher or lower location, memory location. So for that, microprocessor automatically increments or decrements the index registers. To control that, there is a flag, a direction flag represented with DF. The direction flag determines if the index register would be incremented or decremented. So if DF is 0, then that would mean the auto increment mode is set, and each time the string instruction is repeated, SI and DI would be incremented by the number of bytes that have been operated on. For example, if the string instruction is operating on a single byte, then SI and DI would be incremented by 1, and if the data is 2 byte or word, a single word, then SI and DI is incremented by 2. Similarly, if auto decrement mode is set, then that can be set using by setting DF is equal to 1, and that would mean that each time the string instruction is repeated, SI and D are decremented by the number of bytes that have been operated on. For example, if a single byte is moved, then SI and D are decremented by 1, and if 2 bytes are moved, then SI and D are decremented by 2. Compare a string instruction is a useful instruction that compares two sections of memory data as string bytes or string words, and in later microprocessor that can be double word or it can be a quad word. So quad word, two quad word strings are compared in case of 8-byte comparison. Okay, so compare string, just like many other string instruction, has different forms. Compare string B stands for byte, so that means 2 bytes of string data are compared with each other. And in this case, the source of data is in the data segment, and the offset address is provided by the source index register. So first, the physical address of the source operand is calculated, and let we call it MA to the physical address of the source byte. And for that, the data segment starting address is calculated or computed by taking the 16-bit number from the data segment register by left, and then it is left shifted by 1 hexadecimal digit, and the source index offset address is added, so a physical address is calculated for the source operand. Similarly, the destination operand is an extra segment, so extra segment register is used to calculate the starting address of the extra segment, and then DI is used to provide the offset address for the destination. So this would give us the physical address of the destination, which is in the extra segment. That E stands for extra segment. And then the compare string instruction computes or performs the comparison as follows. The byte in the extra segment is subtracted from the byte in the data segment, and the result is not stored anywhere, and this computation only updates or modifies some flag bits. And this comparison is just like comparing the byte at data segment with the byte at the extra segment. So this is a kind of MAD minus MAE, and the result is not stored anywhere, just some flags are modified. And the flags are modified as the following. If the byte at data segment is greater than the byte at extra segment, then obviously no carry, no borrow is required, and so CF is 0, and as the values are not different, so the result is not 0. The values are different, so the result is not 0, and 0 flag is 0. It is set only if the computation would result as 0. So 0 flag would remain at 0, and the result is positive, so sign flag is 0. and if the value at data segment is less than the value at extra segment. So in this subtraction, obviously it would need borrow, so the carry flag is 1, and the result is non-zero, so 0 flag is still 0, and the result would be minus, so and the sign flag is 1. So these 3 flags would be affected, and if the 2 bytes are the same, then obviously no borrow is required, and the result is 0 because as the the two values are the same, so the subtraction would give us 0, so that's why 0 flag is 1. Sign flag is not affected. And as this is byte comparison, so each time a string instruction is executed, the index registers need to be updated. So if the direction flag is 0, that would mean the auto increment mode has been set. So as one byte has been compared, so the DI is incremented by 1, SI is incremented by 1, and if the direction flag is 1, then DI is decremented by 1 and SI is decremented by 1. So depending on the direction flag at this time when this instruction is being executed, either this auto increment mode is used or auto decrement mode is used. And similarly, when in the different form of compare string, which is W, so compare string word, that compares a word of string data at the data segment memory location addressed by SI with a word of data at extra segment memory location addressed by DI. And so the same subtraction occurs, but the difference is that the subtraction happens over 16-bit of data instead of 8-bit of data here. So the flags are affected in the same manner as we just discussed with compare string byte, and similarly for word operation, in case of auto increment mode, DI and SI are incremented by 2. The reason 2 is used because the compare string instruction is operating on 2 bytes, so that's why 2 is incremented, 2 is added with index register. And similarly, if auto decrement mode is used, then 2 is subtracted from both index registers. There are other variation. Compare string D. D stands for double word. This instruction is available in 80386 and above. And similarly, there is compare string Q. Q stands for quad word. So 8 bytes of strings are compared with each other, and this instruction is available in Pentium 4 and above microprocessors. There is a simple procedure that compares a string at line with a string table. So these line and table basically are pointing to the first address of string data. So the contents of the data segment memory location addressed by the source index, which actually is the line, and that is compared with the content of the extra segment memory location addressed by DI, which is actually the starting address of the table. And then let me, okay, sorry. And then a CLD process control instruction is used to clear the direction flag. So here, this instruction is used to set the auto increment mode, and if there is another instruction, and that is STD, to set direction flag, that would choose the auto decrement mode. So depending on the application, in this case, this procedure, the programmer sets auto increment mode using CLD instruction, and after we have the starting address of the first byte of the line is added with the SI, and the first address of the table is added with DI. These instruction offset are just moving the starting address or the offset address of the line with SI and not the value at this line. So offset address is used to move the offset address to SI and DI. And after auto increment mode is set, counter is set to 10, so that repeat instruction would cause the string instruction to be executed 10 times. And there is a repeat prefix is also used, and this repeat prefix is repeat while equal compare string byte. So what this compare string byte would do, that it would compare a byte from the data segment memory location addressed by SI with a byte in the extra segment memory location addressed by DI. And if the two bytes are equal, this repeat while equal instruction would cause this instruction to be repeated again, and each time after each execution, this counter is decremented by 1, and it also checks if the counter is not is equal to 0. As long as the counter is not is equal to 0, and as long as the two bytes are the same, this repeat while equal instruction would cause this instruction to be executed again and again. So eventually it will stop only if CX becomes 0, or it will stop executing this instruction only if there is a mismatch between two bytes. If two bytes are not equal to each other, then this loop will break. So this is a kind of search between these two string data, line and table. Scan string instruction compares a string byte in AL or a word in X with a byte or word in memory, which is the extra segment. So scan string instruction compares accumulator with byte or bytes in the extra segment. It basically subtracts accumulator from the memory without affecting the register in the memory. So actually it is subtracting the memory byte or the memory word from L if it is a byte, or it subtracts the memory word if from X. This instruction is also uses index register DI that provides the offset address for the extra segment of the memory. Here are some different forms of scan string instruction, and the first form of this instruction is scan string byte. So this instruction is operating on byte, and remember that in this instruction is using extra segment with DI to provide the offset address. And to do that, the physical address needs to be calculated first, and the physical address is calculated by taking the 16-bit number from the extra segment register that is left shifted by 1 hexadecimal digit to make it 20-bit, and then the offset address, which is taken from the DI register, is added with it to get a 20-bit physical address of the memory location. And then the byte at that memory location, which is in the extra segment, that physical address is here. That is subtracted from AL because the string instruction is a byte instruction. So it is subtracting 1 byte from the memory, 1 byte in the memory from 1 byte in the accumulator, and that is AL. So this subtraction, the result of this subtraction is not stored anywhere, but this causes some flags to be affected, and the flags are affected just like here. If L is greater than the byte in the memory, then no flag is affected. The carry flag is 0, the 0 flag is 0, the sign flag is 0. And if the value, the byte in accumulator, which is AL, is smaller than the byte from the memory, then this subtraction would need a borrow. So the carry flag is 1, and the result is not 0, so 0 flag is 0, and the result is still positive, so sign flag is 1. Because the result is negative, so sign flag is 1. And if the two values or the two bytes are the same, then no carry is needed, no borrow is needed, so zero carry flag is 0. And as the result is 0, so 0 flag is resist, or it is set to 1, and the sign flag is 0 because the result is still uh, positive. And just like with other instructions, depending on the direction flag, if it is auto increment mode, then one is added with the destination index register, so that it would find to the next higher byte of the extra segment. And if auto decrement mode is set, then one is subtracted from the DI register, because this instruction is operating on a single byte, so that's why one is either added or one is subtracted from the destination index register. In the other variation, the other form of string instruction, scan string instruction, it is operating on word, which is 16-bit or 2 bytes. So in this case, in the same way, the physical address, which is MAE of the extra segment, is calculated as it was calculated before. So it's AZ, the segment number from the extra segment register is left shifted by 1 hexadecimal digit, and that is equivalent to multiplying the 16-bit address with 16 in the decimal system. And the offset address from the DI is added to calculator to compute physical address, 20-bit physical address. And the byte at that physical address, which is represented with MAE, is subtracted from the 2 bytes at this memory location and the next one location, the next higher location, are subtracted. This 16-bit value is subtracted from the accumulator AX, and this calculation modifies 3 flags. So if the value at X is greater than the 16-bit value at MAE and MAE plus 1, then no carry is needed, so no borrow is needed, so carry flag is 0. The result is not 0, so 0 flag is still 0, sign flag is 0. And if X is less than the 16-bit value in the memory, then a borrow would be needed, so that's why carry flag is 1, and the result is non-zero, so 0 flag is 0, and the result would be negative, so that's why sign flag is 1. And if the two words are the same, then carry is not required, borrow is not required, so CF is 0, and the result is 0, so that's why Z 0 flag is 1, and the result is non-negative, so sign flag is 0. And quite the same way, as the instruction is operating on 2 bytes, so the index registers are incremented or decremented by 2 depending on the direction flag. If the direction flag is 0, and then DI is a 2 is added with DI, and if the direction flag is 1, then auto decrement mode is set, and 2 is subtracted from DI. There is a procedure, simple procedure that is using scan string instruction with byte, and it is using repeat and prefix with repeat if not equal. So here this procedure searches the 100 bytes block of the memory in the extra segment for byte 00H. So there is a block of string data, and that block is named as block BLOCK, and that block of 100 bytes is defined in the extra segment. So what we need to do is to first move the starting address of the block to the destination index register, because that is the register to find to the specific location in the extra segment. So the offset prefix is used. So this instruction would move the starting address or the first address of the block to DI. So DI is initialized with the offset address of the block, and then an auto increment mode is used. Auto increment mode is set by clearing the direction flag. So CLD instruction is used to clear the direction flag. So the direction flag is cleared. That means it is set to 0. So that is auto increment mode. So now, depending on the size of the string to be up to on which the instruction is operating, 1 or 2 is added each time the string instruction is executed. So after auto increment mode is set, the counter is initialized, which is CX register. It is initialized to 100 because we want this string instruction to be repeated 100 times, because we want to search 100 bytes of the block. So that's why counter is initialized to 100, because each time the string instruction is repeated, it checks the value in the counter. Exclusive OR is used to L to clear the any value in the L register. If there is any value in the L, it is exclusive OR with itself. It is cleared, or it is set to zeros. So all the bits are now zeros in the L. So we now know that AL, which is accumulator L, maintained or contain 00H. So that's what we want to search for. So we want to search for the byte 00H. So that's why we used exclusive OR LL, and instead of this instruction, we could just use MOV, and we could move L comma 00H. So we would move 00H to L. So both are the same. After moving 00H in the L, now we are ready to scan the accumulator or search the byte in the accumulator in the block of memory in the extra segment. And to do that, repeat while not equal instruction prefix is used with scan string bytes. This scan string byte instruction would now search the byte in accumulator, which is 00H, in the 100 bytes block of memory. So each time this instruction is repeated, the byte in AL, which is subtracted, the byte in the memory, the first byte of the block is subtracted from the byte in the accumulator, which is 00H, just like we discussed here. So this instruction would cause to subtract the first byte of block from the AL, and it would subtract 1 from 100 because this instruction has been executed once. So if repeat while not equal, so if the result, which is here the subtraction, if the result is not 0, it will cause this instruction to be repeated again, to be executed again. And it not only checks if the two values are equal or not, it also checks if the value in the CX register is 0 or not. If it is 0, then it will skip the execution, and if it is non-zero, then it will continue executing this instruction, and and with each execution, as auto increment mode has been set, so a DI, which finds to the byte in the extra segment, is incremented by 1. So that would mean that next byte of the block is compared with the 00H and L, and the same condition check is repeated. And similarly, this process continues until all the bytes of the block of the memory in the extra segment is searched or compared with the 00H. Okay, so this is one application or one example of how scan string byte can be used to search a byte of string data in the 100 bytes block of memory. Load string instruction loads accumulator from the memory, and the memory is the data segment. LODS instruction loads string byte into accumulator L, or it can load a string word into AX register, or in the later microprocessor it can load double word into EX register, or it can load even a quad word into the 64-bit version of the accumulator if available in the microprocessor. And each time it accesses the memory, it is the data segment addressed by the source index register. In the earlier instruction, it was the extra segment, but here the source of the data is taken from the memory. So the source is normally the data segment, and the offset address is provided by the source index register. And after loading the accumulator with 1 byte, or X with L with 1 byte, X with 2 bytes, or EX with 4 bytes, the contents of the source index register are either incremented. If it is auto increment mode, then it is incremented by 1. If L is loaded, it is incremented by 2. If X is loaded, it is incremented by 4. If EX is loaded. And if auto decrement mode is set, that happens when D is 1, then SI is decremented by 1. If L is loaded, it is decremented by 2. If AX is loaded, and it is decremented by 4 if EX is loaded. And the same happens here. If in case of L, it is incremented by 1. In case of X, it is incremented by 2. And in case of EX, it is incremented by 4. So depending on the number of bytes that are loaded, the SI register is incremented or decremented by that number. Just like other scan string instruction, load string instruction also has different forms. And in the first form, load string byte, this instruction loads a byte from the data segment memory location addressed by SI, and it loads or store it in the accumulator L. And the physical address is calculated just like before. The 16-bit value in the data segment register is left shifted by 1 hexadecimal digit, and the offset address SI is added with it, so that the physical address is calculated, and the byte at that physical address, which is in the data segment, is moved to the L, and according to the direction flag, SI is either incremented or SI is either decremented, because 1 byte is moved. And in case of load SW, this instruction is operating on 16-bit of data, so the physical address is calculated the same way, and the 2 bytes at this physical address, that means the byte at this physical address plus the byte at next higher memory location, these 2 bytes are moved to the X register, and the direction flag, according to the direction flag, the source index register is incremented by 2 or decremented by 2. There are other different forms of load S instruction available for the 8086 and above microprocessors. Load SB, as we just saw it, loads a single byte from the data segment memory location addressed by SI to AL, and SI is incremented or decremented by 1. Plus minus means it is either incremented or decremented depending on the direction flag. If the direction flag is 0, it is incremented. If it is 1, then it is decremented. Similarly, load SW is also available. It is loading accumulator AX from the data segment memory location addressed by SI, and after the execution of this instruction, SI is either incremented by 2 or decremented by 2 depending on the direction flag. In the later microprocessor, load SD double word is also available, so this instruction loads the 32-bit or the extended version of the accumulator, which is EX, from the data segment memory location addressed by SI, and the source index register SI is incremented or decremented by 4 because 4 bytes have been moved. And in case of Q letter, a quad word of string data is moved. That is 64-bit data from the data segment memory location addressed by RSI is moved to the 64-bit accumulator, which is RAX. And in case of variables are used instead of these letters B, W, D, Q. Instead of these letters, the string instruction may be used with variables, and then the size of these variables determines if a byte or word or double word of data is being moved from the memory to the accumulator. So if less is a byte, then this would move a single byte of data from the data segment memory location addressed by SI to AL, and SI would be updated by 1. And similarly, if the variable followed load S is a word, then 2 bytes of data are moved from the data segment to X, and SI is incremented by or decremented by 2. And in this case, frog is a variable, and if frog is a double word, then 4 bytes of data are loaded from the memory to EX register. And this is a simple diagram that explains the status of registers: source index register, data segment register, accumulator, 32-bit accumulator, EX, and the status of the data segment after a 16-bit instruction load SW is executed. So this instruction loads a 16-bit data or 1 word of data from the data segment memory location addressed by source index register at that time and the data is moved or loaded to accumulator AX. Because it is a 32-bit, it is a word instruction, so it copies or moves 16-bit data from the memory to a 16-bit register, and which is AX. So it is EX, but the AX part is updated, or 16-bit data from the memory is loaded to the AX register. And this calculation, or these operation happens in this order. First, the 16-bit value from the data segment register is taken. It is left shifted by 1, so a 0 is introduced here, and that is also equivalent to multiplying it with 16 in the decimal. And then the offset address from SI is added. So a physical address or memory address is calculated. That is 11000 here, and this physical address then identifies a location in the data segment, and here in this case as 2 bytes are moved. So this is 1100 memory location that was calculated here. The physical address was calculated here, but as the data transfer is 2 byte, so the first byte is taken from the address calculated, and the second byte is taken from the next higher address, which is this one. So the value that would be moved is a 0 and 3, 2. So these 2 bytes are moved to accumulator, and so the 16-bit part of the accumulator, which is AX, is updated. So A032 is moved from the data segment memory location addressed by this SI register. Similarly, there is a store a string instruction. So store string instruction stores accumulator in the extra segment memory location addressed by DI. Store instruction can store the 8-bit part of accumulator, which is AL. It can store in the memory the 16-bit part of the accumulator, which is AX, and it can also store the 32-bit part of the accumulator, which is EX. In the later microprocessor, it can store the extended version of the accumulator as well. So it stores a byte or word or double word in the extra segment memory location addressed by DI, and after accumulator are stored in the memory, the contents of the destination index register are updated. It is either incremented or by 1, 2, or 4 if the auto increment mode is set, or it is decremented by 1, 2, or 4 if the auto decrement mode is set. The value that is added or subtracted from the DI is the number of bytes that are loaded from the accumulator, that are moved from the accumulator, just like the instruction, the string instruction that we talked about in this lecture.